Seems to be a long, deep winter this year. Yeah. Yeah, I'm sad that we're not taking students to New Zealand. That was always a great place to be in March. Sorry?
Did that stop around COVID?
It got cancelled because of COVID. It stopped. We went last time we went was 23. We stopped because the university now want us to, instead of just doing it seat of our pants, us organising it, us driving the vans, picking up the students who travel on their own to Auckland and then dropping them off at the airport. They want us to make have it done through a third-party tour group for risk assessment. They're worried about someone getting hurt. Which I guess is useful. Makes it much more expensive. Would make it much more expensive, and makes it much less fun, I think. So we don't. It was a great trip. It was a great trip.
Where do you guys go?
In New Zealand. Land in Auckland, we'd go to I was just talking about it in the last class. Why don't we do that for a change? There we go. Grab everyone in Auckland. At noon on a Monday, we drive down to Huntly, which is a thermal power station, about 1 gigawatt, and visit there in the afternoon on Monday. After grabbing lunch at the grocery store, we go to Raglan, which is a surfer town, and stay there overnight. We go into a wind farm above Raglan on the morning of the Tuesday. Then we drive to Hamilton for lunch, and then we go to a dam on the river that comes out of Taupo, whose name escapes me, the Arapuni Dam. Stay in Taupo overnight. Go to geothermal plants on the Wednesday. Thursday, well, this is a different tour. Thursday we've gone up to Rotorua, which is a spa town, and then we go back into Auckland and back. So, yeah. Huntly Power Station. Control room. This is a long time ago.
Is it a big what's kind of power station?
It's thermal, it's coal. Yeah, it was, these are coal boilers back here and turbines, and then they added a gas turbine running on natural gas. Last time we were there in 23, I think they were almost shut down because they had a drought and didn't have any water to be able to run through the turbines. Cabooses for accommodation, wind farm, Arapuni Dam, and geothermal plants. Rotokawa, I think. Geothermal generation, control room, geothermal drilling rig, blowout pretenders.
Is it cold up there?
No, it's warmer than State College at that time of year. These were actually taken in May, these ones, but at March it would always be warmer. It would be 60.
No, isn't that's their fault. Isn't New Zealand in the southern hemisphere? Wouldn't that be their
It's their fall.
Yeah.
Yes, their fall. It'd be their winter right now, going into fall. Yeah. But when we went with the students, it's March, so it's almost 12-hour days, almost the equinox, which must be the 21st of March, right? Yeah, not terrible, not terrible. Don't fall asleep. Chirpy, less chirpy. Christchurch after the earthquake. This is 2013. I think the earthquake was 2011. Took a long time. I think this is a waterfall where everyone wanted to go, which is, what's the strange movie with people with short people with strange feet? Hobbits? Hobbits, yeah.
You went to the Lord Lord of the Rings filming location.
This was apparently. We were there for another reason. We went past it.
Yeah.
Hydroelectric plant, Auckland. Bungee jumping, I guess, if you want to do it. So. But alas, I won't be there. Emily, are you alive?
What?
You're not paying attention, I know that, but are you alive
I am alive.
after your big activity over the weekend? Well done.
Thank you.
Are the lights back on in DR?
Oh, you know about that?
I know everything. I'm all.
Some places.
They had a big grid failure, yeah? 80% down? Yeah. Yeah. Good. Good to hear. Oh, you got to keep up with stuff.
Yeah, you are.
All right. Questions, comments? Good the order before we get going. We'll have this week's classes, Thursdays as well, and then no classes, but the midterm on Tuesday, a week today, and then no class on Thursday, right? You know. So. Stuff online, you know, it's a pretty limited field in terms of what you have to go through. It won't go through material you haven't covered yet, obviously. So I think you're in good shape. All right. We made the point last time that we could look at the behavior of solutes traveling in the subsurface and their delay in arriving at places, and also how reduced their concentration was. In terms of recap, you've seen these diagrams before, right? So I don't know if I need to, I'll draw it anyway, why not? You know what I'm going to draw. And we could look at residence time distributions as they came out. So this would be time, this would be concentration, and time. This would always be turned on at some time t0. And we could define this behavior in terms of plug flow, where we could define how far it goes downstream, and arrival, and the effects of finite dispersion. And what else? Yeah, I guess we made the case that we can define behavior in terms of concentration change with time is equal to dispersion divided by a retardation factor times dt2c dx squared minus advective velocity divided by retardation factor dc dx. So advection, dispersion, we could define this retardation factor as 1 plus bulk density times the distribution coefficient. Can't remember whether they call it uppercase k or lowercase. And either porosity or volumetric moisture content. If it's fully saturated, it's porosity, which would go into here. And we could define the behavior in terms of this length traveled would be equal to velocity times time of retardation. If retardation is equal to 1, then it's just as we had before. And T is equal to length times retardation divided by velocity, advective velocity. This is in the x direction. And so if retardation is equal to 1, which it is when there's no sorption onto the static grains, then these equations reduce to the ones we had before. I guess we also made the point that we can define these two important parameters of Peclet number, which is velocity times length over dispersion, and Courant number, which we call this pore volume, which was, I can't remember, velocity times time divided by length. Velocity is equal to length over time, times time. And so this is equal to 1. If it's 1 pore volume, then it should arrive, and that gives us this point here. But I suppose we also made the point that we could also divide this velocity. So this velocity means that it would be physically delayed, and so the retarded breakthrough would be here, because r would be greater than 1. And if that was the case, it would also arrive later. And so in terms of these numbers, we could take the velocity, which is operated on by this retardation factor, and the dispersion, which is also operated on it, and we divide this by retardation, and we divide this by retardation for this, which doesn't change it. Velocity times length over dispersion. But in this case it does, because it's only this top value which is divided through. And so this would be advective velocity times time over length and retardation. So Peclet number doesn't change. Courant number or pore volumes does change. But with these values, we can use those relationships that we drew the figures for. And so if you remember, if I can keep them both on the same page, we have this residence time distribution, and it was drawn in terms of relative concentration, I guess 1 and 0, pore volumes, T sub r, which would be this, and it would be equations like this. So this would be 1. This would be Peclet number equals infinity. Peclet number equal 10, say, and Peclet number equal 1, for instance, just as an idea. So we can use these expressions we have. We just have to use Peclet numbers and Courant numbers that include the retardation factor to account for this behavior, and it only turns up in this parameter here. Peclet numbers would be still the same. Okay, right, that's all I'm going to say. So what we did last time was we looked at the controls on Peclet, on the distribution coefficient. We defined this distribution coefficient as equal to the concentration that's sorbed on the solid divided by the concentration in the liquid, in the water, by definition. And so we could always measure this. This was an isotherm, as we called it. And so long as we can get this, we can make some predictions in this behavior. We didn't come up with any smart ways to do this, except we did use the natural gradient tracer test to realize that if we did that natural gradient tracer test and the plume went less far downwind as it did for a conservative solute, then we could use the ratios of the velocities as a retardation coefficient. That's physically what it means. It's the velocity of a conservative solute relative to the velocity of a non-conservative solute, and different non-conservative solutes, we chose two, might have different velocities, as we saw. But if we know how far they've traveled, that in a given time, we know the velocities are in the same ratio, and therefore the retardation coefficients are in the same ratio. And we could use that to be able to take the definition of retardation coefficient to switch it around to get KD. Didn't talk much about the numbers, but if we did that for the Borden site, for carbon tetrachloride and tetrachloroethylene, we got values of KD, which are this. And that's useful because then we could use that in our forward modeling to figure out what the plume would look like if we looked 10 years hence or earlier, if we want to be able to project behavior. So that's not very convenient because it's a very big outlay to be able to do something like this. So the question is whether there's a better way to get a value of distribution coefficient. And of course there is. And so what you can use as a predictor of sorption, and therefore of K sub D, are these two methods. So use oxygenol water partition coefficients or solubility of that solvent in water, a table you can pick up in library text to be able to make an estimate of this distribution coefficient without either running the test in the laboratory, which we could imagine doing, or measuring retardation factor in the field. So that's what we'll talk about today. So we'll talk about getting it from octanol water partition coefficients and solubilities. We'll talk about what we might want to do if you have multiple species in trying to get into the water, as you do at Smithville, for instance, as you've been looking at. And then we can also look at if we know how much mass is in situ and we know how much mass the water can carry, because we'll find out from Raoult's law, if we have multiple species competing to get into the water, it can't go in at the full concentration of its solubility. It'll be somewhat less. That's really what Raoult's law says. And so we'll use that to calculate what the solubilities, effective solubilities would be, which we'll call S sub E's. And if we know what the effective solubilities are and we run water through the system, then we should be able to take a stab at how long it would take to clean up the aquifer if we just do pump and treat. And we can also make some refined estimates of how much solute might be in place if we account both for the amount that's present dissolved in water, which will just be the volume of the aquifer multiplied by the porosity multiplied by the solubility, right? We'll come back to this. You can imagine that the volume of the aquifer times the porosity is the constant total volume in the aquifer as void volume. And that if that water that occupies that is at a particular solubility, then the product of those two gives you the mass in place. But of course it doesn't give you the mass in place because there's some that's sorbed onto the solid substrate, and we have to account for that. So the mass in place will be slightly larger because of that. So we'll see how to do it. And it's related to the retardation coefficient. What's going on? That's not a problem. Reese, are you alive?
I am
Good. You look tired.
a little bit.
I know that's not a compliment. People will say to me, "Oh, you look tired there." I say that's not a compliment because that's what I always look like. But you don't always look like that. Anyway, well done, by the way. Back to this. So the basic thesis is this: is that we made the point that organic carbon sorbs these solvents. That's why we use carbon filters to be able to take them out of drinking water. So if it turns out that most of the sorption that's going to occur in the aquifer is going to be due to the presence of carbon, then we can use the sorption capability of carbon and the amount of carbon in the aquifer to be able to figure out what's going on. We can only do that if there's enough carbon in the aquifer so that we can neglect the small amount that would get sorbed onto the quartz grains in the sand aquifer. And so the basic idea is that it will sorb onto the solid, but it won't sorb in very much onto the solid. But if there's no carbon in the aquifer, then by using this approximation for large amounts of fraction of organic carbon will give you an error because there won't be any on the carbon, but there will be some on the solid, and you won't account for it by using this. So if you have lots of organic carbon in the aquifer, more than 0.1%, then we can use the product of such things as the KD, just by rearranging this expression, is equal to the fraction of organic carbon as a decimal multiplied by the organic carbon partition coefficient, KOC. In other words, the propensity of the carbon of the solute to want to sorb onto carbon. We know how much of it is as a portion of the aquifer. We know its propensity to sorb, and therefore that together gives us the KD value. If it's less than this percentage, then most of the sorption will be onto the mineral quartz. And so by using this equation to calculate it, it completely ignores the stuff on the mineral quartz. If there's zero organic carbon, this will give a KD of 0, no sorption, no retardation, and therefore we'll be missing the amount that's on the solid skeleton of the aquifer. So that's what our plan is, and it's relatively straightforward. So the idea is that we can use empirical correlations to link this term here, which we need, organic carbon partition coefficient, I guess which is stated here. We can get this by two possible ways, perhaps more, I don't know. One is to be able to work out the octanol water partition coefficient, and that's a measure of how octanol dissolves in water, what its solubility is, in other words. And that can be used to estimate the organic carbon partition coefficient. Or we could use the solubility of the solute in water to be able to identify this. So in both cases, we want to figure out what KOC is, organic carbon partition coefficient. If we have that, we have this. And if we know how much organic carbon, we have this. And if we have that, we know that the retardation is equal to 1 plus bulk density over porosity, K sub D. And this is in milliliters per gram, or grams per kilogram, typically. So it's a recipe. So horrible slides that come out of Feder. I know none of you bought Feder, or I think none of you bought Feder, which is fine. And so the idea is that we can use some empirical expressions which define this term in terms of some coefficients. And it's just a recipe for its manipulation. So you take whatever the substance is, you find out what its solubility is, you plug it into this expression, you find out what log KOC is, you tend to the exit to get KOC, and once you have KOC, you have KD. That's it. And so it's a recipe. And so, I don't know whether you can see that or not. So if you want to do that, there's a whole series of these empirical relationships. They're for different compounds. We're going to look here at ethylbenzene in this particular case for this expression here, which apparently it can be applied to. It looks like this. And it needs a value of the solubility of ethylbenzene for this. The solubility of ethylbenzene is this number here. It's in 140 milligrams per liter. So this is parts per million, I guess, right? A gram is 1,000th of a liter. A milligram is a millionth of a liter. in terms of density. So this is parts per million. If you put that in, so this is kind of dimensionless, so it's 10 to the minus 6. Then if it's 140 milligrams per liter, if you define this as this term here, it'll be 3.64 minus 0.55 times the solubility, which is 140 milligrams per liter. The logarithm of 140 is somewhere between 10 to the 2 and 10 to the 3. 100 and 1,000, it's 10 to the 2.15. And if you take this expression and plug it in here, which is what this is here, then the log KOC is equal to 2.46. If you, again, 10 to the exit, this is going to be 10 to the power 2.46, which is somewhere between 100 and 1,000, and it's actually almost 300. So if KOC is this, then the distribution coefficient, KD, is going to be equal to the fraction of organic carbon multiplied by 288 milligrams per liter. Have to use these units. That's not dimensions. So this would be parts per million, ppm, for this term here anyway. Okay. So that's one way to do it. The other way to do it is to use the octanol water partition coefficient. And that could be used, got from a textbook. And so this here is this number here. If we do it for benzene, if you can see it, it's 2.13 is the log octanol water partition coefficient. I should get a better version of this slide. 10 to the exit again is 10 to the power 2.13, which is 135. Substitute it into this again in milligrams per liter rather. Substitute it into here, so 0.63 times 135 is 82.98, and that's what this number should be. The table's wrong. And so it's just a matter of being able to figure out exactly what these numbers are, either from using the solubility or by using the defined value of the octanol water coefficient available from many, many textbooks. And so once you have that, then you can calculate what KD would be. And we didn't dwell on this. We didn't do this last Thursday, but you could calculate for Borden. Borden's a very clean aquifer. Maybe it has 0.02%, so that's 0.0002, right? As a percentage. And so we shouldn't use it, but if we try using it, we can calculate what the octanol organic carbon partition coefficient is. We can do it from solubility. I don't know whether for carbon tet was one of the compounds. Don't know whether it was here. I thought I got it from this table, but perhaps not. Tetrachlor, I think. This. Is this it? 106.38? Oh no, solubility, not OW. Is that it here? Could be 150. Let's see if it is 150. No, it's 805. Don't know where it came from. Take it on trust anyway. So if the solubility is 805 milligrams per liter, you can use the same expression we had before. Log of 805 is going to be somewhere between 100 and 1,000. 10 to the 2 and 10 to the 3. It's closer to 1,000, so it's closer to 10 to the 3. 2.9. In other words, this value of 805 is actually equal to 10 to the power 2.9. Substitute in here, do the math, ends up being 2.04 in terms of log KOC. If you 10 to the x this, so 10 to the 2.04 is just a bit bigger than 100, turns out to be 110. So the organic carbon partition coefficient is this in milliliters per gram. And if we multiply this value by the fraction of organic carbon, 0.02%, you end up with 0.02 milliliters per gram. So that's the value of KD. So the option is that now, since we did Borden, we didn't spend much time on it, for a carbon tetrachloride, this is this. We realized that the plume had only gone a fraction of the distance. At 2 years, it's gone 57 meters for the conservative solute and something like 25 meters for the non-conservative. I guess it wasn't quite 25. It was less than 25 because we have a number bigger than 2, which is this. So this is our retardation factor. So if we go back and from a known value of retardation factor, figure out what this is, if we know what the bulk density of the aquifer is, kilograms per meter cubed, 2,000 kilograms per meter cubed, or 2 kilograms per liter. Porosity of 30% as decimal. It turns out that the value of K sub D in milliliters per gram should be about 0.213 milliliters per gram. And so that is from the real site where we're not making any assumptions about the amount of organic carbon. So if we compare this 0.213 versus the value that we got from the other system, from doing it the other way, this is much, much higher than our calculation for using this relationship. And the reason for that is, as we stated earlier, is we're assuming that all the sorption is on organic carbon, but there's almost no organic carbon in the system. So we're completely missing the amount. This will give us a very low ball estimate, because actually, if the organic carbon is 0%, then this would actually be 0. And so it's giving us a low ball estimate. And so the true one for the aquifer includes the amount that's sorbed onto the quartz that it's flowing past, and it's not sorbed on, and only a small amount is sorbed onto carbon because there's such a small proportion. So that's why these numbers logically do not equate. This is the correct number. This is absolutely incorrect because we've used it in an inappropriate context, I guess. Okay, so that's that. We saw that for Borden, the retardation coefficients were between, they were less than 5, was it? And greater than 2. They're within this range. If we looked at the values for the natural gradient tracer test, I don't recall right now. Yeah, so 4.38 and 2.5-ish. So they're in that range. If you look at a bunch of well-known, perhaps infamous, contaminated sites around the globe, then you also get some estimates of these numbers. And so you see that they range, they have to be bigger than 1. So you see some of them are close to that, but are in the 2s and 3s. Some get as high as 10-ish. This looks like it's 23. I thought there was a 33 that I saw before. And so these are a bunch of big Superfund sites. Palo Alto must be semiconductor plant contamination. Switzerland, I'm not sure we looked at this. Gloucester land, yeah, we did actually. Federer's book had this. We looked at an example where we talked about lateral dispersion from a landfill, and that was the Gloucester landfill in Ontario, not so far away from Borden. Don't know where this one is. This is Borden, natural gradient experiment, Two of the ones we looked at were for carbon tet and tetrachloroethylene, 1.9 to 2.5, 2.7 to 5.9. Our estimates were 2.5 and 4.3, I think, right? So we're in that ballpark. Moffett Field Naval Air Station, don't know what that is. Otis Air Force Base is a contaminated site on Cape Cod, and all these things. But I guess you get some appreciation for these magnitudes. That's the only reason I turn to this. They're all greater than 1. Sometimes they're in the low digits, 1, 2, 3. Sometimes they go up to 10, and sometimes they can be very high. And so we'll come back to these different sites at the end of our class today and see if we look at how much was spilt or disposed of at each of these sites, how big the plume can be. And of course, that's the big deal, right? If you spill 1 barrel of solvent at one of these sites, once it's spread out into a plume, you have to harvest this huge volume of fluid in the aquifer to be able to recover it. And so that's what makes the huge, huge expense. So we talked about what the magnitudes would be for K sub D, distribution coefficients, to be able to use in this relationship. So we can estimate what retardation would be. So far we've done it only for a single compound, but now what we might do is look at what the case would be as in for Borden, not Borden, Smithville, which is also in Ontario, if we have multiple species competing at the same time to be dissolved in water. And so for that, we use Raoult's law. I'm sure you've seen it in the past. The effective solubility, when you have multiple solutes, is equal to the solubility of that solute on its own in water, the free pure phase solubility, if you like, multiplied by a fraction, and the fraction is defined in terms of molecular mole fraction. And that is because individual molecules are combining with each other one-on-one, and so it should be mole fraction that is the index, not weight fraction or not volume fraction, but mole fraction. And so it's a pretty straightforward number to be able to calculate, and that is we know what these free phase solubilities are. It was just 835, was it, for CTET, carbon tetrachloride, etc. I think for TCE it's 1100 is a number I often used, but we know what this number is. But if we know it's present with other solvents, then we have to reduce the solubility accordingly because they're competing to dissolve. And so this is just the calculation for Smithville. So TCE, TCB, and PCBs, plus mineral oils. And so these percentages you've already seen, they're in weight percentages. And so if we know what the molecular weights are, then we can calculate for 100 grams of cocktail exactly what the proportions of these components would be. So the formula weight for TCE is 131 grams per mole, I guess. And so if we take the 2 weight percent and divide by the molecular weight, that means we have this number of moles in the cocktail, 0.0152. If we take the 10 weight percent of TCB and know its molecular weight, then the ratio of those two numbers, 10 over 181, gives us 0.055. And that's the number of moles we have of that component. We do it for PCB. I do it for mineral oils with the molecular weight. I don't know if this is right or not. And then these are the total number of moles we have in the system. And so if we have 0.0152 moles of TCE in a total of 0.677, then the ratio of those two, which is here, is just the mole fraction. And so we can calculate the mole fraction. So instead of being 2% by weight, it's 2.2% by mole fraction. Instead of being 10% by weight, it's 8.12. So it's the appropriate scale. They're not very different from each other. Perhaps you could get away with using these given all the uncertainties you might have in the representation, but these are at the actual magnitudes. And so that means that for TCE, if we only have 2% and the mole fraction's 2.2% or 0.022 multiplied by the solubility, 1100 or 1060, is 23 milligrams per liter. So the effective solubility, instead of being 1060, is much less because it's present only in a small portion. This is present in a larger portion, so again, the product of the mole fraction multiplied by its solubility gives you an effective solubility for each of these. And so the bottom line, I suppose, is that if you're looking at the plume going down gradient at some distance and there is a concentration, maybe concentration rather than relative concentration, then the concentration for TCE would be a small number, and it would go down some certain distance. So this would be solubility 1. I guess this would be this. The solubility of the other components might be this. This is higher, or no, it's not higher. So I guess switch those around. I'm just going to relabel them. So this would be S1, this would be S2, so this would be S1, this would be S2, this would be S3. Which would be down here. So there's two things to be cognizant of. So this would be coming from, so this is present at free phase within the aquifer. It dissolves into the water. It dissolves at these solubilities. And these would be the upstream concentrations that would be defined for it going downstream. So that's the first thing that we can determine for this. If we know the mole fractions and the solubilities, we can always calculate this upstream concentration. We can also, if we know what the KD values are for S1, then, which would be KD1, then we can also calculate the retardation for component 1 as being equal to 1 plus bulk density, porosity, or volumetric moisture content times KD. And so these KDs would be different for each of the solutes, and so they might travel different distances downrange in a given time. So T equals, I don't know, 1 year. And so the two things we can calculate from this are that, one, we know that they'll dissolve at different concentrations, and that would be their equilibrium solubility corrected for their proportions in the free phase product. So this would be in the cocktail of dry cleaning fluid, these percentages, and the rates at which they get carried downstream would be conditioned by the retardation number. A smaller retardation number, the further it's gone. So this would be R value small, and this would be R value big, in terms of just a shorthand. Okay? And so we can calculate that. And we can use simple plug flow models to represent that. And I suppose if you had a compliance point here, you'd realize that you have only pristine water. If you had a compliance point here, you'd realize that only S2 had arrived in a low concentration, and that S3 had not yet arrived, and S1 had not yet arrived. And if you have a compliance point here, you'd see that they'd all arrived by the time you looked at this thing. So that's just a pictorial representation of that. Okay? All right. And finally, so now, if we know what concentrations they will dissolve in aqueous solution at. This would be the maximum concentration they will dissolve at. Then if we have water flowing through an aquifer, taking out the free phase components, then we could calculate how long it would take to clean up the aquifer, just very straightforwardly. And so there are some simple models that we might be able to use. So this is representing the idea that if we have stuff that's done this in the subsurface, right? We talked about these little lenses in the system, and so I don't know if I have this. And so we talked about there being some kind of chimney, a smear chimney, and through this chimney we could have water passing. I guess I meant to do it with this one. So this would be a velocity, advective velocity of water traveling through here. Then if we kind of idealize this as something, and one idealization could be that we take it to look like this. With water coming out of this face here. So a bit like this. So this would be the place where we had stuff present within the chimney. I guess the water table would have to be here, right, for this to happen. This is saturated flow. And so that's one way that we could look at how long it would take to be able to deplete all of the free product that's present, that's held at residual saturation, free phase residual saturation in this. We could also look at a different model, in which case we had water going above and below a lens. Perhaps it wouldn't go below, because if it's sitting on a capillary barrier, there might not be much water flowing underneath it. But certainly above it, I've kind of messed this diagram up, above it where it's arrived here and water can flow across it, then it might have this geometry. So we can look at these two different geometries to say something about the rates of removal. And so we could define for each of them both the mass rates of removal and the total mass that's present. And I guess if we look at mass rate of removal is equal to mass divided by time. So time is equal to mass divided by mass rate of removal. Just simple relationships. So if we can do two things, if we know how much mass is present within the system, so if we know saturations and porosities and the volume of this cube, you know how to do that. And if we now turn our attention to see what the mass rates of removal are for these two separate systems, then we have enough to say how long it would take to remediate the aquifer. So these are just two different models. So the first one is really kind of cleaning up the smeared chimney, if you like. This is just what I said already, and that is that the total mass within the system divided by the mass rate of removal gives us the time to clean it up. The mass rate of removal we could get from the advective velocity times the porosity. So this actually, since we know that advective velocity is equal to the Darcy velocity divided by porosity, then this product of advective velocity and porosity is just the Darcy velocity. And so the Darcy velocity multiplied by the cross-sectional flow area. Lots of sniffles. I've got one as well. This is just the volumetric flow rate, right? Darcy velocity and cross-sectional area of flow. Cross-sectional area of flow is this upstream or downstream area. And so if you know what this solubility concentration is, then you can do that. So this could be the solubility, or more likely, it could be the effective solubility of species I. In other words, these are the effective solubilities. better off using these because they represent if you have multiple solutes. So this would be the effective solubility, and it could also be these numbers multiplied by some factor, as we'll talk a bit later, because it might not be very effective at picking this up. You can imagine that if you flowed water through this very quickly, it wouldn't have enough residence time in this volume to be able to dissolve all the material up to its full loading into the water. If it's almost stagnant in here, it would reach that maximum concentration, and so there's some number between 0 and infinity at which you would take up a full loading of this, which would be this magnitude. If it flows faster than that magnitude, it will only have a portion of it. And you could do a calculation for this. So if you know that the Darcy velocity would be equal to hydraulic conductivity times dH dx, I guess we also know that this is equal to permeability, viscosity of water, dP dx. And if you know from the slope of the water table above it, for instance, that this is dx and dH, they're the same. So in other words, if you know the hydraulic gradient, this is a hydraulic gradient, dH dx, just a number, 1 in 100. Hydraulic conductivity, a reasonable number for porosity. You can get an advective velocity or a Darcy velocity. And if you know what that Darcy velocity is, you get Q. And if you know what the effective solubility is, you can get this term here. And you can use those to make a calculation. I won't bore you with the details, but if you use these numbers and do the calculation for a reasonable flow rate, for the density of PCE, and for a reasonable solubility, I think this is just a tenth of the free phase solubility. You get almost 1,000 years to dissolve it all out. So pump and treat is in perpetuity. It does biodegrade, but it takes a long time to be able to dissolve it out. And so great if you want to pump and treat and fend off a lawsuit, but it won't actually clean up the aquifer very quickly. So distributed flow within a volume in the chimney. The other one would be a puddle sitting down in different locations within the chimney or at the base of the capillary barrier where you have flow over the top. And so this has limited contact with it because it only touches it on the top and the bottom. And so you could imagine that this would, by Fickian diffusion, diffuse into the water that's flowing around it, and then be carried with the bulk motion of the water as it goes downstream. So that's what this second solution is. Water flows past here. It creates hydrodynamic dispersion and diffusion to let the free product dissolve into the water and move by the concentration gradient. It moves by the concentration gradient, then gets advected downstream by the water that's flowing past it. And so all this is a solution that accounts for that. I guess it looks at this kind of, let me do it red. Did you know on notability? Oh, you're not the notability fiend, are you? It's your other colleague who isn't here today.
Oh.
Notability, yes,
Oh.
Stephanie. I found a trick to be able to change colors without on the keyboard. Yeah, fine. And I just did it. You can tell her that I've mastered notability. Just trying to impress you with my IT skills. Not with that one. So this is the puddle that sits at the bottom of, or on top of the capillary barrier. So the idea is that we can take a column, which is unit area within this system, and we can look at diffusion of that into the water that's flowing past it. So this is by dispersion, escaping like this. This is by advective transport around it. This is I call it two different things here. Pool, this is the length of the pool. Uppercase L. And this is the height of the pool, which is doesn't matter. HP. So this length here controls the dispersion or diffusion into the water that's traveling around it. And this is the advective velocity of the water. This is dispersion of the solute. And it's just a closed form solution. So the length is the length across the puddle. The height is the height of the puddle. This is the surface average mass transfer rate. So in other words, this is the mass transfer that comes out both top and bottom per unit area, meter by meter, I guess, into the water that flows past it. And it's given by the dispersion coefficient, which you know. 1 over plume length divided by 10, right, for this. Advective velocity, 10 to the minus 9 meters squared per second here. Advective velocity, which we'd need to know. The length of the plume, because that length of the plume defines how much residence time this water has in gathering the stuff that diffuses up into it. That's why it's controlled there. CSAT would be the effective solubility of species I, whatever that is, and NE would be the porosity of the system. So you have all those here. So again, if you have the mass rate of removal, so that would be mass per meter squared per unit time by this, then if you know how much mass is present within this puddle, then you're able to calculate the time it would take to deplete it. So this is the mass within the puddle. So what would this be? This would be the mass per unit area. So this is mass of that per unit area. So this would be the height of the puddle. Porosity times saturation would be the mass in the pore space. Multiplied by the height of the column. So this would also be HP. So the mass per unit volume multiplied by the height would give you the mass per unit area. Sorry, the volume of that. So that'll give the volume, right? Volume per unit area. Multiply volume by density. You have mass. And if you divide that by the mass rate of removal, you have the time taken to deplete it. So, all to make the point that you could imagine this occurring in a couple of different geometries. One where you have it flowing through the smear zone, picking it up, the magnitude of the effective solubility being conditioned by the residence time. Likewise, this one is also conditioned by the residence time in whether it picks up enough, if it's flowing slowly enough across the top to pick up the bulk of this diffusing mass into the system. And the reason for looking at the residence time as it goes across the top is that if you do an experiment where you look at taking an aquarium and you put a puddle on the bottom of TCE and you fill the aquarium up with sand and flow from one side to the other, then as a result of the solubility of TCE in water, if you flow it at different velocities, so 1 meter a day, these are advective velocities, I guess. So this would be a residence time of 1.5 days. travels 1 meter in a day. The pool, no, 0.15 days, right? No, that's right. 150 centimeters is 1.5 meters, right? 1.5 days, 2.3 days, etc. So if the velocity is larger and the residence time is longer, no, velocity is larger, residence time is shorter, you'd expect the concentrations, relative concentrations, to decrease. And so if it spends less time in contact with the material it's flying past, then you'd expect the concentration to be reduced. And so these concentrations are 10% of the magnitudes. There's no magic number in 10%, but it's just that at these particular velocities, it spends insufficient time in contact with this pool, both because it has to diffuse into it and because the residence time is very short, that it only picks up a fraction of the concentration. So if you wanted to calculate what the true concentration would be, it would be equal to the effective solubility of compound I, which effective solubility is equal to the free phase solubility multiplied by the mole fraction of I. So this is the free phase solubility you get from a reference text. You multiply it by the mole fraction to get the effective solubility, and then maybe you multiply it by something else. It seems very hokey, doesn't it, to be able to get the effect for this residence time distribution. So all things that might be you might want to be aware of. So in estimating these things, so 10% is not a bad number. So finally, the final thing we wanted to calculate was how much mass is present in place. And so we talked about mass removal rates, that's what we just discussed. So how do we calculate the mass in place? So we suggested before, and I guess in these last calculations, that the mass was going to be equal to the volume of the pore space multiplied by the saturation. So this is saturation, not solubility. Times the density. And so this would be equal to the volume of the reservoir times the porosity, which would be this term. This would be the solubility, saturation, how much of the pore space is filled with that component, and what is its density. And so that is a reasonable estimate of the total mass that's available, but what it doesn't include is it doesn't include the amount that is attached to the solid. So we've said that a distribution coefficient defines the ratio of how much is present on the solid versus how much is present in the water. And the way that we would do that is by this little experiment where we take porous medium, we dump in a component which has a certain concentration in the liquid and a certain concentration that sorbs onto the solid. We do it with a certain concentration in the liquid and see how much attaches to the solid. We do it again with a higher concentration in the liquid and see how much attaches to the solid. It gives us 2 data points. And we do this. And then this value here is given by the distribution coefficient and 1. And so I guess we know that even though there's a concentration in the liquid form, which we can measure here, we'd expect it to be some function of the solubility. I guess this should be effective solubility, by the way. But there's also some mass that's present on the solid grains. And so in the same way that if we throw in fluid of a certain concentration will dissolve a certain amount on the solid, attach a certain amount of the solid. Since it's reversible, if we then throw clean water in here, then we'll go back to this concentration here. And so this is reversible. If we flush this plume out, so there's no dissolved component on it, then the stuff that's attached to this quartz will want to come back into the fluid, the traveling fluid, and be dragged out of the system. And so if we do put pristine water through the system, we'll get not only the stuff that's present within the dissolved component, but also the stuff that comes off that is sorbed to the quartz. And so we need to account for that. And it's not very difficult to account for that. It works out to be a very neat expression. I think it's neat. And this is it. So you can imagine that the total mass is equal to the solubility. So we've called this S effective times the porosity times the volume of the aquifer. So these together represent pore volume. Times a mass per unit volume gives us a mass. So this is the dissolved mass that's in the aquifer sitting on its lonesome. But there's a portion of the mass which is attached to the aquifer, the grains. And that's the concentration on the grains, the bulk density of the aquifer, and the same volume of the aquifer that's filled with the contaminated plume. This is the volume of the plume. The total volume of the plume, including, you know, if the plume is 100 meters long and the aquifer is 10 meters high and 10 meters wide, it's 100 times 10 times 10, not anything to do with the volume that's inside that, excluding the solids. If we take the definition of distribution coefficient, which we just had, was that KD is equal to C star over C. That's what this is. If we substitute for this distribution concentration on the solid into here, multiply top and bottom by porosity, because you have porosity here, and rearrange it, I won't bore you with the details, but it's a neat expression because everything drops out, and it's just the mass is equal to the solubility, effective solubility of whatever the compound is, the porosity of the aquifer, the total volume of the aquifer, and the retardation coefficient. So neatly, I think, this accounts for the 1, so the retardation coefficient is equal to 1 plus bulk density of the aquifer, KD, and porosity. So this represents the part that's present dissolved, which is this part. This part represents the parts that attach to the solid, which is this part. And it just scales in these proportions. And so it all gets included together. So I think it's kind of neat. This is retardation coefficient. What else? I was going to say something else. This is the bulk density of the aquifer. So 2,000 kilograms per cubic meter, which goes in here. And I guess you don't need it here because this is a, the solubility takes care of the mass that turns up here. Okay? That's it, I think. Not going to talk about this. Don't need to talk about that. That's it. So now we know everything dealing with the dissolved components in the groundwater zone. 4.1 was dealing with the mechanisms by which sorption occurs. 4.2 is talking about how to estimate it from useful parameters such as octanol water partition coefficient and solubility, how to accommodate competing solubilities from compounds in water, and to calculate back of the envelope rates of removal from kind of closed form solutions, and also to calculate, if we want to figure out how much is in place, we can calculate that as well. And I guess the parting shot is to realize the role of entropy in all this. So entropy, I guess, means that disorder always increases. So those contaminated waste sites that we looked at previous are kind of drawn out here in terms of the plumes. These are plan views of the plumes that developed at each of these. Cape Cod was Otis Air Force Base. Gloucester was a landfill in Ontario. This was solvents in California. This is probably the Denver Arsenal near Denver. And if you look at calculating from the shapes of the plumes, their aerial plan view, so the volume of the plume is equal to its area times its height. And if we know what the volume of the plume is, was it the bottom here? If we know the total volume of the plume, we know the solubilities of those compounds which are present, we know the porosity, and we know the retardation factor, which we had here, had retardation factors for all these compounds, which are different for all these different locations. Then we can calculate what the mass present in the aquifer is. And it turns out that to get these very significant, big, contaminated aquifer portions, it's not very much stuff that goes into it. So these are 72 55-gallon drums. 7 55-gallon drums. 0.4 of a 55-gallon drums. And the relative scales aren't here, but they're hundreds of meters, perhaps kilometers in size to get to these. And it takes very little to do that, 0.6 of a drum. And so that just makes the point that very easy to deal with when it's concentrated, not solution, free phase concentrate in a drum, not so easy to deal with when you have a huge volume of water at very low concentration that you have to somehow do something with to get it out of the ground. That's the main point. So that's it. So you just need to count for the part that's attached to the solid. Next time we'll talk about the vadose zone. And so I guess we'll make the point that to get to being in the groundwater zone, usually stuff starts on the surface, goes across the vadose zone, and ends up in the groundwater zone. If it's an NAPL, it will only sit on top of the groundwater zone because it's lighter than water. If it's a NAPL, it will go through it. And we can try and estimate the rates at which it would end up being transmitted to the groundwater zone after transiting the vapor zone, the vadose zone. And it turns out that the biggest mechanism by which it goes through is by being dissolved in rainwater, which ultimately hits the groundwater table. So I'm leaving it at that. Great, thanks very much.